I'd like to introduce this afternoon's keynote speaker, Clint Crosier, Director of the AWS Aerospace and Satellite Business, which was established by Amazon Web Services to accelerate innovation in the global aerospace and satellite industry. He leads a global team that's dedicated to working alongside commercial and government space customers to provide tailored, secure, cost-effective, cloud-based solutions to help solve their toughest challenges. And prior to joining AWS, Clint was in the Air Force with a career spanning 33 years and U.S. Space Force as well. And his background includes a broad range of experience in space operations, including a one-year deployment to the Middle East as U.S. Central Command Director of Space Forces. Prior to retiring from the military, he served as Major General and was lead planner and architect of U.S. Space Force. So it's my deep pleasure to hand it over to fellow Amazonian, Clint Crosier.
Good afternoon, everybody. It's great to see you all here, and I really enjoyed participating in the hybrid space architecture. Good, you can hear me now? Excellent. Yeah, for those folks online. I really appreciate it. I got here a little earlier today, and I sat in on the hybrid space architecture working group, and that was really fascinating. I bounced back and forth to the working group here, too, and I took a look at some of what was going on in here, including the things that were on the board, and it's all fascinating. So anyway, let me just say thank you to NewSpace Nexus. Thank you to SSIB. Thank you to Space Northwest. Thank you to DIU, AFRL, the whole team that's responsible for putting this workshop together. I really appreciate the opportunity to be with you today. I want to talk for about 20, 25 minutes, and then I'll spend 8 or 10 or 12 minutes or whatever you guys decide on a few questions, if you have any. But I also recognize you've been going at it all day. And I think I'm the only thing that stands between you and the reception a little bit later on today, too. So I'm always mindful of that. So I have been in the space business almost 37 years now, 33 years on active duty in the U.S. Air Force, and then a key role in creating the U.S. Space Force. If you see me at the reception, I'm happy to tell you the story about the time I got called in to see the Chief of Staff of the Air Force one day. And the chief said, "Hey, Clint, President Trump's really serious about creating a Space Force. He wants a plan to stand up a new military service, and he wants it in 30 days, and we need you to do it." And I reminded him, "Hey, Chief, maybe you forgot, but I'm retiring in June." And he put his hand on my shoulder and he said, "Yeah, not anymore." So anyway, I can tell you that story another time. But so 33 years on active duty, flying satellites, launching rockets, my whole career in space. And so I had a wonderful opportunity about 4 years ago as I retired from the U.S. Air Force and the U.S. Space Force. AWS called and they said, "Hey, Clint, we've got a really innovative and interesting idea. At AWS, we see the rapid growth of the space industry and the space domain. And we believe advanced cloud technologies like artificial intelligence, machine learning, advanced data analytics, quantum computing, generative AI, all those things that you will know about can play a key role in moving the space industry forward into the future. But we don't have a centralized or holistic way that we go about addressing all of those parts of the aerospace and satellite business. And so we want to create a new business focused solely and specifically on the aerospace and satellite domain and figuring how we bring all these cloud-based technologies to that industry." And so thus was born the global aerospace and satellite business that I have the privilege of leading and leads me to being here with you today. Like I said, I'll talk for about 20 minutes or so and then take some questions. Now, how do I go backwards? You showed me how to go forward, but you didn't show me how to go backwards, and I double-clicked. So let's see if I can make that happen. Yeah, I'm way in the wrong way now. I can just try the backward arrow usually works. So I'm there. Okay, terrific. Called her up for nothing. Sorry about that. Thanks, Ariel. So let me just share it. You all know most of this, but let me share some thoughts with you, too. In the 37 years I've been part of the space industry, I have never seen a more exciting time to be part of the space industry than we're living in right now today. By any measure that you want to take, whether you want to look at the number of organizations, companies, and countries that are moving into the space industry and space domain in the last number of years. And by the way, by my count, there are more than 75 countries today that have their own space agencies. Think about that. When I was growing up, the only countries that could operate in space were the United States and the Soviet Union. You remember those days? Now we have 75 countries around the world that have their own space agencies and are either building and operating their own satellites or having somebody build and operate satellites for them. So that's a game changer in the industry. When you think about the money that's spent today, and McKinsey and the World Economic Forum just released a study a couple of weeks ago, a month or so ago, that they are highlighting that there will be a $1.8 trillion global space economy by 2035. And that's an increase of $600 billion by 2035 from the last update they did in 2020. So, I mean, the industry is growing. Or whether you look at the number of satellites that are being launched every year, and you can pick your study, but there are studies that say we'll increase by 3 times the number of satellites on orbit over the next 10 years, by 5 times, by 10 times. I'll just go with the middle and say 5 times, right? We'll have 5 times more satellites on orbit over the next 10 years than we have today. When you look at not only SpaceX operating today, but these mega constellations like Amazon Kuiper that is on the way. OneWeb's growing their constellation. I'm supporting a company called Rivada Space, and they're putting a 600 satellite constellation up, and more. So things are getting really, really dynamic, and they're really growing as we look at the space industry. Now, 2 of the key themes that you've laid out for the workshops today are the outer net and new propulsion systems. And so I'll spend most of my time remaining talking about the outer net, but I did hear some of the conversation that was going on here in this room with the previous working group about propulsion capabilities, and I will share with you, there's a company out of the UK called MagDrive that applied for and was selected for the AWS 2022 Space Accelerator. And so I've had the privilege of 4 years in a row now running the AWS Global Space Accelerator, because at AWS, we believe that startups represent some of the most exciting innovation and experimentation that's going on anywhere in the industry today. And by the way, when organizations like DIU and AFRL and Space RCO let money towards those things, we think it creates exciting innovation across that startup community. But we launched one a few years ago, and we've run it 4 years now. And MagDrive, working on electric propulsion for space systems, space capabilities, satellites, and spacecraft, which I think is really interesting. And graduating from the AWS Space Accelerator, they moved on to the DIU AFRL sponsored Hyperspace Challenge in 2023 and did some interesting work in that event too. So there are companies right now today working, as you probably know, new and novel space concepts and MagDrive for propulsion. And MagDrive in particular is using AWS and our high performance compute capability to do all the modeling and simulations for how their electric propulsion system would work, not only thermally and mechanically as an entity itself, as an integrated network, but also in the dynamic environment of space against the cycles of the sun and recharging solar arrays and all those sorts of things. So some really interesting things going on. So that's space propulsion. As we talk about the outer net, though, some really interesting things we see going on out there at AWS. And by the way, I want to say right up front on outer net, just to clarify, we in the other room, in the hybrid space architecture, we're talking about outer net, and we all had a common definition of what we meant by outer net. For those of you that might have been in this room, the outer net is essentially the ability to compute off-world, compute off-network, right? So space-based computation, moving the computation environment, the global network integration environment into space. And the reason I say that is because I mentioned Rivada Space Network. Rivada Space Network is one of AWS's customers, and they are actually building a 600 satellite constellation that they call the outer net, capital N, capital E, capital T, trademark, right? So I just want to be careful when we say outer net. I'm not referring to my friends at Rivada who are building some innovative space-based, networked, mesh, optical, linked constellation that never requires you move data down to the Earth. You do it all in space. That's different than the outer net we've been talking about today here, although there are some overlaps, but I wanted to be clear about that. When we think about the outer net, though, what we're really talking about is we're starting to talk about edge and edge compute, right? AWS for the last decade has been pushing the boundaries of what we call edge computing. And frankly, edge computing simply means if you're not standing in a data center and you're doing cloud compute, you're doing edge computing, right? The only place you're not doing edge computing is if you're physically in a data center. Now, most of us who are a little bit older like me, we grew up in the environment that was the only place you could do computing was in a data center, right? But what we found is we were locked into a physical infrastructure. We didn't have operational backups because it was too expensive to build multiple data centers everywhere we want to go. And by the way, we don't have data centers at forward deployed locations like maritime operations centers or air operations centers or tactical operations centers from the military side, or seaborne and remote areas and all those sorts of things. So AWS is working hard over the last decade perfecting edge computing capabilities where we, rather than making users bring their data to the cloud, which is expensive, increases latency, causes all sorts of logistics challenges, we've decided we're going to move the cloud to our users, decreases latency, increases security, increases innovation. So that's AWS Edge Computing. And one of the examples here on the left-hand side is the AWS MDC, Modular Data Center. So this is an edge compute device. On the larger end, we've got smaller edge compute devices we call the Snow family, like snow cones and that sort of capability. This is a larger one. I mean, if I was standing there, you could line up about 6 of me across. So that's how large this is. But this is essentially an AWS data center in a box that's deployable, that's mobile, that's rugged, and you can deploy out into a military operational environment, which would support things like JADC2, Joint All-Domain Command and Control, All-Domain Operations, Extended Edge Network. And we work with our friends SES Networks, which is a global SATCOM capability that operates primarily in GEO and MEO. And so now this is SATCOM connected as well. So it can either operate providing AI, ML, advanced compute, storage, et cetera, capability in a deployed remote environment, either connected to SATCOM, or it can operate and sustain itself for a period of time disconnected from the rest of the cloud as well. So we're already seeing these sort of edge compute capabilities move into military uses as well as they are in maritime uses for commercial shipping and farming uses and those sorts of things. So as we think about moving the edge to our customers where our customers needs it, and we've demonstrated a track record of doing that for a decade, when it comes to that organization I told you that I lead, the Aerospace and Satellite Organization, my customers aren't on this planet, right? In the time that we spend together looking at operational missions and capabilities, we're focused off the planet. And so when I think about edge computing, I don't just stop at forward deploying AWS edge compute capabilities to forward disconnected regions. I think about deploying where my customers need them, and my customers need them on orbit in space. And how's that for forward edge, remote, disconnected, and deployed, right? But that's where we need these capabilities, because at AWS, just as we have seen, and I don't mean this to sound like an AWS commercial, I really don't, but just when you think about cloud, let me just say cloud. When you think about cloud, and everybody knows we're using cloud in the financial industry, in the healthcare industry, in the transportation industry, again, AI, ML, advanced data analytics, quantum computing, high performance compute. We need those modern technologies to fuel all of our industries around the globe today. We need those just as much when we think about the future capabilities. We were talking in the other room, as we move into the future, there are companies right now like Blue Origin that is working on Orbital Reef, which is going to be a low Earth orbit commercial space station where they'll have everything from the ability to do in-space manufacturing and in-space servicing to medical science and experiments to R&D to commercial tourism and travel, right? Axiom Space is also building the Axiom Station, which will be a low Earth orbit space station designed to do the same thing. And by the way, talk about a groundbreaking capability. Axiom was the first organization in the world that got a commercial contract to replenish a module of the International Space Station. The ISS was always a government-funded operation and organization. It's still government-funded, but for the first time, you've got a commercial company in Axiom who is building and operating on AWS, taking advantage of our cloud capability, who's building a replacement module. So as you think about asteroid mining, as you think about building and operating, building satellites in orbit, right? The most expensive and challenging proposition right now today in launching a satellite on orbit is the launch mission, right? I used to launch Titan and Atlas rockets from Vandenberg, excuse me, putting satellites up for the National Reconnaissance Office and for NASA, right? The single most violent, challenging, and expensive part of the entire mission is the launch operation. Now, if you think about it in terms of terrestrial example, here's what we don't do, right? This will be kind of funny, I hope. Here's what we don't do. We don't build ships in the desert and then ship them to the ocean, you know, via rail and then launch them out at sea, right? But that's what we do here on Earth. We build satellites on the Earth and then launch them into space so that they can operate in space. What if we can get to a capability with the Axiom Space Station and Blue Origin Orbital Reef and all these other nodes and networks, especially as NASA moves to cislunar capability and a human encampment and habitat on the moon? What if we could build and operate space parts and space pieces in orbit and not have to move them across the desert to get into their operating domain? That's a game changer. When we think about, as we talked about in the other room, when we think about asteroid mining and be able to harvest precious materials off asteroids or the surface of the moon, or maybe one day the surface of the Mars, that's a game changer. When we think about in-space service and manufacturing, or ISAM, right? My whole career, when we launched a satellite, in fact, I was talking to somebody earlier about Milstar, that we operated Milstar at different times. But one of the first Milstar satellites launched and it failed to achieve its operational orbit, and it was sort of a lost satellite because once it was on orbit in the wrong orbit, there's nothing you could do about it. What if I could send a satellite or a spacecraft from the Axiom Space Station or the Blue Orbit Space Station with a service module on it to go up to the Milstar satellite or any other satellite and repair a solar array or give it more gas or propulsion capability, or swap out a module to improve the optical sensor and increase my ability, or swap out the electro-optical sensor with an ISR sensor, or whatever the case may be. In-space service and manufacturing is going to be a game changer to how we do all these capabilities, right? All of these require autonomy, do they not, right? Require robotics, right? That's what space is essentially and has always been. It's a robotic capability. It requires autonomy, robotics, advanced compute, high-performance compute, data analytics, and you don't want to have to move all that from orbit to the Earth. As an example, the Mars rover that NASA has on the surface of Mars right now today is operating on AWS. It's bringing all that data, the Perseverance rover, it's moving around on the surface of the planet, it's taking soil samples, it's sending all that data 300 million miles back to the Earth. It's being processed in the AWS cloud, and then 300 million miles back to Mars again, only, and I say this somewhat facetiously, only to tell the rover, move 8 feet to the left and drill there. Right? We can't afford to do that, right? We can't afford to do that when we're talking about real-time missions like automated maneuver and threat detection, automated maneuver response to threats, and robotics required for close approaches or conjunction approaches, right? You can't afford to push it. You can't afford the latency. You can't afford the bandwidth. So all that's going to happen in space. All that has to happen in space. Edge computing in space, the outer net, the ability to do advanced cloud computing in space, just like we do advanced cloud computing here on the Earth. And so AWS has put a lot of time, energy, and focus in that, not only in our team, but in all those customers that we support helping build that out. As an example, AWS and Project Kuiper is working with DIU right now on the hybrid space architecture in a couple of contracts that we're doing along with some of our customers to identify how you do the network orchestration and the network management. And we talked about that in the other room. You know, one of the challenges is when you try to stitch together a constellation of disparate companies across disparate bands in different orbits with different technologies and different ground station capabilities. How do you stitch all that together? How do you manage it in real time, securely, right? And it requires a network management system. So AWS, Kuiper, DIU working on some of those capabilities so that we can provide that outer net in space, if you will, to support all these important missions, national defense, intelligence missions, and global commercial missions that are going to be game changers moving into the future. I also would like to share with you, it's operating a little slowly. I got latency here. I need to move it closer to the cloud. Try to do it again. Advance, there we go. I also want to talk about off-world compute in some real-world on-orbit demonstrations and experiments that we've run in the last couple of years. So the picture on the left is actually an artist's rendition of a D-Orbit satellite. So D-Orbit is a company that builds and operates hyperspectral satellites out of Italy, out of Europe, and we partnered with D-Orbit, and we built a cloud computing capability, purpose-built hardware and software, along with our friends at Unibap that builds rad-hard, rad-tolerant circuit boards. And so we built a purpose-built hardware, software capability, integrated into D-Orbit's hyperspectral satellite. D-Orbit launched it onto orbit, and then we ran a number of experiments where we pre-processed hyperspectral imagery doing things like filtering out clouds, because as you know, with electro-optical and hyperspectral, cloud cover gets in the way and ruins your imaging capabilities. So we screened out clouds. We also did pre-processing of data. We gave it ML algorithms, and we said, don't include it in the deck that you download if cloud cover is X or Y. Don't include it if a change condition hasn't been met, et cetera. And what we found in this experiment is we reduced by 42% the downlink requirements to meet 100% mission requirements of the hyperspectral imaging satellite, reduced by 42% the downlink requirements with 100% mission success. That's a game changer when you think that you can cut downlink requirements approximately in half on a single satellite by pre-processing the data in orbit rather than pushing it all to the ground. And then you think again about, asteroid mining and advanced robotics and in-space service and manufacturing and what something like that can do. As another example, the one on the right here is Orbital Reef, and AWS has partnered with Blue Origin in building Orbital Reef, and we are essentially cloud enabling the Blue Origin Orbital Reef platform. It is going to be a cloud node in the sky, where AWS is providing the advanced cloud computing capability, the network connection, the orchestration layer to support all those missions that are going to go on in this commercial space park with Blue Origin. And when you think about the ability to do on-orbit compute and cloud computing capability, I'll give you another example. Some of you might know that right now today on the ISS, we do a lot of medical science experimentation on ISS, a lot of genome sequencing, a lot of medicine development, that sort of thing, because the results you get in microgravity are more pure than when you get under the influence of the Earth's atmosphere, and you get different results that are important, I'm told. I'm not the expert in it, but important in developing new medicines and those sorts of things, especially with genome sequencing. So what the Axiom and Blue Origin and NASA folks tell me is a typical day is they'll run an experiment that takes about an hour to run with genome sequencing. And then because of the limited bandwidth between the ISS and the ground nodes, it could take as much as 12 to 18 hours to download all the data from the genome sequencing experiment. They run the data on the AWS cloud in about 20 minutes and then upload all the instructions, just like I told you with Mars and the Perseverance, and they run it back. And that whole cycle takes about 24 hours. So you're essentially getting one experiment every 24 hours. Not because of the time it takes to run the experiment or analyze the data, but simply because of the time it takes to transit back and forth to the Earth with limited bandwidth pipes. Move that cloud computing capability on orbit like what we did with an AWS snow cone in the Axiom space station last year, and suddenly now you're running that same genome sequencing experiment. You're processing it in 20 to 30 minutes on the ISS, and then you're setting up for the next experiment, and you're increasing anywhere from 10 to 15 times the amount of science time that's available on the ISS for medical experimentation by doing the computing and analysis on orbit rather than pushing all the way to the Earth. These are game-changing capabilities that we see the need for the outer net, advanced computing, advanced network integration and protocols, and things that we're really, really excited about to see for the future. As we think about continued development, I'll share with you one of the things we identified in the previous forum a little bit earlier was by the time, whatever the number, 4X, 5X, 12X, whatever the number is of the number of satellites that are going to be launched over the next decade, that much more than we have today, right? I said 5X. I picked 5X. So if there are 5X more satellites in LEO today than or tomorrow than there are today, there's some 1,000 today. There'll be 5,000, 7,000, 10,000 in orbit 10 years from now. Think about the need to do real-time space surveillance, space tracking, collision avoidance, space traffic management capability, right? My whole career flying satellites, space is big. It's most likely two objects won't run into each other. However, every now and then they do. But we have just enough global surveillance capability and command and control capability to be able to identify a potential collision 10 to 12 hours ahead of time and take action 2 to 3 hours ahead of time to mitigate or reduce the probability of collision. When you have 5 times, 10 times the number of satellites in orbit, you won't be able to do that. And you won't get 12 hours notice before you have a potential conjunction. So Leo Labs, which is another company that builds and operates on AWS, perhaps you know them, they do low Earth orbit space traffic management and collision avoidance, and they got way out in front of the rest of the industry. They were the first company that I know of that recognized proliferated LEO and the growth in LEO was going to require significantly different global space traffic management capabilities. And they built out a global system of radars around the world that they used to provide the best in the world that I know of commercial capability in LEO space traffic management. So as Leo Labs looked at how they were going to do this mission, they ran into the same problem. They said, look, if we think all VL, right, and that's space SSA, SDA lingo, but all VL, if you look at all 6,000 objects on space versus all 6,000 objects on space in the satellite catalog, and then you do a 24-hour run prediction across plus or minus 3 to 5% perturbation and everything in between, it gives you all the potential collisions going on in the next 24 hours. And so as they looked at the incredible compute capability required for all VL against 6,000 objects over the next 24-hour period, they assessed it would take them approximately 8 hours with the best computers available to run that whole model. So think about that, what it looked like. Leo Labs calls you and they said, hey, you've got a potential conjunction 18 hours from now. And you say, okay, thank you very much. And for those of you that are experts, I know I'm going to use the wrong language, but I know that ahead of time, so just forgive me. But to make it easier, so what will you will say to them is, okay, should I maneuver up, down, left, or right? Right, delta V, and I understand that. But should I maneuver up, down, left, or right? And the answer is, okay, let us go run all those. So 8 hours to run the global all VL perturbation run if you maneuver up, another 8 hours, right? And now it's 32 hours to run these 4 COAs to come back and tell you which one minimizes the probability of your collision. But you remember, the premise of this conversation was this happens 12 hours from now. And so 8 times 4, 32. I don't have 32 hours to go run these. They moved all that to the AWS cloud using our top 40 supercomputer speed. And now real-time space traffic management is made possible for the first time ever, in that instead of 8 hours, it takes them a grand total of 10 seconds. I know you thought I was going to say 10 minutes. I trick everybody when I tell that story. 10 seconds, from 8 hours to 10 seconds. So now, in the span of a 2-minute phone call, Leo Labs calls you up and says, you've got a potential collision. And you say, should I maneuver up, down, left, or right? And they say, stand by. And in the time of a 2-minute phone call, they run all 4 of those COAs and come back and tell you COA D most maximizes the limit of a collision or minimizes the probability of collision. You should do that one. That's real-time space traffic management that didn't exist before until you get tools like advanced cloud computing, high-performance compute, that allow you to the speed and complexity necessary to take thousands and thousands of volumes of data and turn it into real-time space traffic management and collision avoidance. So that's a really exciting use. And by the way, that's space sustainability. We talk about sustainability a lot here on the Earth, right? And Amazon is a big proponent. We have the Amazon Sustainability, Global Sustainability Initiative, everything else. I think about space sustainability, right? The Kessler effect, debris creates debris, right? How do you avoid all that? And the first thing you do to avoid all that is real-time, secure, operational global space traffic management and collision avoidance. So that's really exciting. Last thing I'll share with you, and then I'll get into some Q&A if you want to, is I want to talk about another really exciting topic that I'm spending a lot of time on nowadays, and that's generative AI. And I know people throw these words around a lot, so let me just, pardon me if you already know this, but just a short tutorial on the difference between AI and generative AI, right? Artificial intelligence will look at patterns in your data and say, okay, because we saw this pattern happen 5 times over the last 12 days, we are assessing AI that it's going to happen again with this probability, and if it doesn't happen, then we're going to assess that that's a malfunction or it's an anomaly or something like that. So artificial intelligence analyzes data, observes pattern, predicts patterns, and then it can tell you when you've got a pattern that doesn't seem to match the predictions or the probabilities. That's artificial intelligence. It's backed up by machine learning because the only way you get to those predictions is machine learning and high performance compute against all that data. And by the way, that's how you go from 8 hours to 10 seconds on that probability, right? You have to have the machine learning models that were trained and everything else. But that's artificial intelligence. Generative artificial intelligence, or generative AI, the word generative tells you what you need to know. It's able to generate brand new thoughts and ideas that never existed before. So I could have told you, if you gave me enough time and enough compute power, what the probabilities are of this pattern repeating itself. The problem is I don't have 12 days and an infinite number of computers to do it, right? So that's where AI solves the problem. Generative AI allows you to bring wholly new concepts and ideas to the table. As an example, the first one, revolutionary spacecraft design. I can sit down in front of a Gen AI computer like AWS Bedrock, and I can say, I want to build a satellite, and I want it to weigh no more than 150 kilograms, and I want it to operate for at least 7 years on orbit, and I want it to have the propulsion to have a 99.29 probability of efficiency and performance. I want it to be able to carry an optical sensor and an ISR sensor. I want the failure rate to be X or Y. I want it to be able to operate at least 3 times around the globe without having to recharge the solar rays. I can feed all that to it, and then I can hit compute, and I can step back, and I can come back in the morning, and it will have generated, generative AI, generated design concepts that I could have never thought of before. Wholly new thoughts and ideas. That's why what you're seeing people doing in generative AI today is you see a lot of art, right? Paint me a picture of Clint Crosier standing on the surface of Mars playing the drums, right? I'm a drummer. So, and I've done that. I've actually done that. And it creates a really cool picture. Never has been built before, right? Nobody's ever created a picture of Clint Crosier standing on the surface of Mars playing drums. So it's a wholly new thing, and that's art. Now think about when you move that to spacecraft design. And you're no longer limited to only the designs your engineers can come up with. You're limited to whole new things, and we're starting to see some funky parts being developed. Right? Parts that look like some sort of strange amoebic feature under a microscope, but that's actually the least amount of mass and the largest amount of tensile strength and reduces the volume to the maximum point that it meets your operational needs. These are incredible things that generative AI can do. It also allows you to optimize your testing scenarios with digital twins and others, because you build a digital twin of your system. We were talking about constellation management in the other room. So let's say we have 1,000 satellites we want to interoperate together. We want it to be self-healing. How do you model when one satellite goes out? Where's all the traffic around the world? Where's the highest use case and need? Where are the highest priority users? What are my coverages in that current satellite constellation? And where am I going to route the traffic to provide the best self-healing performance? I can't do that, but generative AI can go out and develop wholly new constellation management concepts and processes that we never considered before, and provide the capability to do that self-healing, real-time integration, and ubiquitous nature, just like your cell phone. If wherever I go, I turn on my cell phone and it works, whether I know what network I'm on or not. The only way you can do that in the future with these large nodes of constellation is using things like generative AI. There's a few other uses that I think are interesting, but I've hit the highlights, and I'll spare you those in the interest of time. But in my view, artificial intelligence and generative AI, generative artificial intelligence, are going to be the 2 biggest game changers in the way we do space operations in the future. And again, if you just think about the nature of it, it's disconnected, it's remote, it's robotic, it's automated, it's autonomous. It has to be self-healing. It has to be able to make decisions. Think about, again, real-time threat detection and automated maneuver, right? All those things using generative AI, those are going to be game changers for the future. And that's where we see some of the really exciting ways we're going to be able to use the cloud and cloud computing capability into the future, not only for the outer net, but as the brief example I gave, for satellite propulsion improvement and capability as well. So what I always leave our customers with on my last slide here is sort of my battle cry, my tagline when I sit down with customers is, to the stars, through the cloud. We are seeing amazing innovation. As we built this aerospace and satellite team 4 years ago, when AWS said, Clint, we think advanced cloud technologies can be key to the future of the aerospace and space industry, but we need to figure out how to apply them. That's what we've been doing over the last 4 years. And every time we sit down with a space company and say, hey, have you thought about using AI for this? Have you thought about using ML for that? Have you thought about data analytics for this? Have you thought about how you'd bring advanced quantum computing to doing real-time space traffic management? Every time we do that, we're essentially telling our customers, to the stars, through the cloud, and it's a really exciting initiative. So I will pause there, and I will take any questions that you all might have. Thank you. Yes, sir, right here. There's a microphone coming for.
One of the things about when you're looking at the kind of computations that you could do, because like if you look at the devices that we have in the Amazon cloud, right? Some of those things are easily approaching 1.5 kilowatts per device, right?
Yeah.
So you're looking at 10 kilowatt servers coming up like within, a year, right? So we know how powerful that is, right? Now you're talking about having, 500 kilowatt tanks, right? We're not going to have that in space. So if we're using simpler, lower wattage, SOCs and building arrays of that for a space cloud, right? If you're doing training, we're back to kind of what we have on terrestrial, right? The problem is for a lot of problems, you get hallucinations, right? Especially if problems have to do with, like, if you look at, tiles on spacecraft, right? So if you're re-entering, you want to know, is it safe to re-enter? People's lives are at stake, right? You can't really do that kind of stuff with AI. You got to do physical simulation. And if you look at the kind of compute that you have on terrestrial, you get like less than 10% utilization. So you get that on the ground. What are we going to do in space?
Yeah, so you threw a lot at me there, I guess. Let me just try to tackle a couple of those. So when I think about artificial intelligence, and again, I'll come from the standpoint of 33 years active duty in intelligence and military operations and joint command and control and deployed downrange, with bad guys shooting rockets at me in Iraq and Afghanistan. You are not going to replace the human in the loop when you're doing human qualified space operations, or when you're doing military operations that can be lethal in nature, right? You're not going to replace the human in the loop, and I would never advocate that you do that. But what you can do is significantly increase the probability that the human in the loop can make a decision quickly with confidence that it's the highest probability of being the right decision. And so I think that's a game changer all by itself. Tiles on the space station. If I can get eyes on the tiles and do a physical inspection, if I can send an astronaut out, and I'd love to do that. But what if I can't do that for some reason, right? Then I'd love to be able to take all the available data. I'd love to be able to crunch it against the latest scientific models, high performance compute as quickly, as efficiently as processed, and then have the system tell me, Clint, here's the range of probabilities across your course of actions, right? So I love that.
Oh, I'm sorry, I wasn't clear. What I was basically saying is if you're running a simulated physics, right? Because it's expensive enough to upload and download from the cost on the ground, right?
Oh, sure.
Can you imagine doing that in space? It's not going to happen, right? So,
Yeah,
so the point was, when you have generating massive amounts of data, right? Let's say you're doing this simulation in space, you're generating huge amount of data. You don't want to transfer that to the ground, right? So if you're simulating it, right, in space, to figure out if something is safe to re-enter or not. I mean, that's how Columbia, right, disintegrated, right? They took a chance on it re-entering and it didn't survive. So my question was, we get so low utilization because it's not an AI problem. All the chips are designed for AI nowadays, right? The clouds are designed for AI. Now you're trying to do another problem and the load utilization is so low. How do you even make cloud computing in space for that application practical?
Yeah, and so sorry if I misunderstood your first question, although I think I made an interesting point even when I misunderstood your question. But to that point about utilization and that sort of thing, if you think about what we did when I told you about how we took a snow cone and we put it on the ISS and we ran experiments across that, that was a commercial off-the-shelf capability, right? We don't want to do that. We won't be able to do that, right? It gives you the art of the possible in terms of what can you do when you have cloud computing capability on orbit. But we will necessarily have to modify capabilities so that they'll operate most effectively in their environment. And oh, by the way, in terms of quantity of power production and power distribution, that's why the other theme of this conference is so important when you think about new propulsion or power generation capabilities, because I won't have an unlimited amount of power in space the way I sometimes potentially do here on Earth, right? We're typically not limited with power generation except in remote locations. So when I don't have that, how do I create new power production capabilities? Likely most solar, right? The one thing that's readily available when I'm on orbit is solar power, right? So we're going to have to come up with new techniques, new ideas to harvest all that. But what I love is that we're beginning of stages of understanding how to do that, what the key requirements and capabilities are, and starting to prove out some of the concepts about what you can do when you can enable that capability. So there's still a lot of technology to be developed for sure. But I think we're at a really exciting place.
Thanks, Clint. Is AWS Ground Station part of your business unit? And if so, could you just give us a brief update on that?
Yeah, so AWS Ground Station is what we call Ground Station as a Service. And really the whole premise of the cloud, frankly, the whole premise of the cloud, for those of you that might not be that familiar with it, is don't build your own global infrastructure of servers and hardware, an army of people to sustain it, maintain it, support it, upgrade it, secure it, everything else. It's millions and millions of dollars to build out a single data center and do all those things. Right now, if you think about you're operating on a global scale or in space on a global scale with multiple redundant and resilient backups, you could be in the tens of millions of dollars. So the idea behind the cloud is don't build all that infrastructure. Leverage AWS, who already has all that infrastructure available. We sustain it, we maintain it, we secure it, we stand by it, and you can just focus on your differentiating capability. What makes your company the best in providing transportation or medical services or financial analysis, right? That's the basic premise and proposition of the cloud. Ground Station is the same. It costs millions of dollars to be able to go out and build a global infrastructure to use for ground stations. Don't spend your precious limited capital doing that. Rather, leverage the AWS Ground Station as a Service and put all your time, energy, and attention on making your sensor more capability or more capable. Now, there are other organizations like KSAT and SSC who offer Ground Station as a Service model, and we respect those. In many ways, we're working with those. But the one advantage that our customers who do come to AWS tell us is it's of great benefit to them because we build all of our AWS ground stations such that they're nearly located or co-located to an AWS data center, and we have 100 megabit per second fiber connecting them. And so once you land your data into an AWS ground station, it's nearly instantaneously available in the cloud to run some 220 global cloud-based services like AI, ML, advanced data analytics on it, and we can push that data anywhere in the world with low and reduced latency. And in today's environment, latency is the new coin of the realm, right? It's not just NIRS used to be, in electro-optical, it was always about NIRS, and NIRS is still important, but we're seeing now, especially for military and intelligence users, reduced latency is becoming as important or more important than NIRS. In some cases. So those are kind of the things. We've got 11 global ground stations around the globe today and a number of customers that are really happy with that capability. Yeah. Yes, sir.
Fascinating presentation, sir. Thank you for presenting it today.
Thank you.
I would like to go back to the point where you were talking about the real-time traffic management for satellites.
Yeah.
You managed to do that very fast, within 10 seconds. Fantastic. But what can you tell us about the cost of the operation and what would be the economic model that would make sense? I mean, who pays for that capability?
Yeah.
And does it make sense?
Yeah. So the cost, I'll give you a couple of answers on cost. First of all, one of the things, and again, I don't mean this to sound like an AWS commercial, but the basic proposition of the cloud, right? The basic proposition is, for Leo Labs, for instance, when they leverage our high-performance compute to provide that answer in 10 seconds instead of 8, they are charged per minute of their HPC usage. So if they need to use, 100 clusters for 4 minutes, they reach in, they grab those, they run those, and then they hand them right back to us. For them to operate the same thing on premises, they would have to go out and build all that capability and then pay for it even every minute it's not being used. With AWS, you pay by the minute only those services that you consume. So that makes it manageable. Most companies tell us it's some 20 to 30% of the total cost of building and operating their own model using AWS. The other thing that's really exciting about that is the flexibility. For instance, if they have 100 users in a given day, they can reach in and fire up 10 cores, right? If 5 years from now they've got 1,000 customers because of the proliferation in Leo, they can reach in and grab 500 cores. Either way, they pay by the minute and they hand it back to us when they're done. So they're able to scale up and scale down with precision rather than worrying about overestimating their usage requirements and buying too much equipment, or underestimating and not buying enough equipment and then not being able to satisfy a customer's capacity needs because they underestimated what the overall capacity would be. So customers tell us it's 20 to 30% of the cost of building it and managing themselves, which is a big economic factor. But Leo Labs, in this case, Leo Labs pays for that cost. Now, do they probably build that into the service of what they provide? Sure, it's a cost of doing business for Leo Labs, but that's essentially the cost model. Okay, last question, maybe one or two more. Okay,
Yeah,
go
go
ahead.
Hi, Clint. Rick Mommer, DIU. You mentioned.
Thanks for the really important work DIU does in this space, by the way.
Oh,
Really, and the sponsorship of the conference too. I've hung out with Bucky Buto a couple of different times, and I appreciate how DIU has leaned into the space industry. Thanks.
Thank you. And I appreciate the work you guys are doing with hybrid space architecture and the partners that we have together on that. So on that vein, we have tremendous resources terrestrially for compute, led by companies such as yourself. I think we can all agree that we'd like to see those resources be available in space to space-based assets. I know you and your team are putting more effort and thought into how to make that a reality than anyone. So my question for you is, what are some of the big barriers, difficulties? What are the big challenges to making that a reality sooner rather than later? And are there things that we can start attacking now?
Yeah, thanks for that. And by the way, I want to be clear too. I wouldn't necessarily move all compute to space, by the way, right? If latency isn't a concern for you and you have enough bandwidth over a sufficient period of time to run your capability, it's probably more cost effective for you to do. Maybe not, but it might be more cost effective to download it, right? But what we're talking about is all these new missions, hyperspectral threat detection, right? Hyperspectral missiles and those sort of hyperspectral. Hypersonic, thank you, sorry. I knew I said it wrong. Hypersonic missile detection and response and all those things. We think about all the things I talked about requiring automation and robotics. So where latency is key and where bandwidth is limited, that's going to be the sweet spot of those capabilities. So I don't advocate you move everything to space compute, but there are going to be a subset of things like human encampments on the moon. You're not going to want to have to push all that data to make a critical decision, you know, about a life-saving procedure or capability. Does the system shut down and move over to the emergency oxygen supply? You don't want to have to move all that to the earth to make it right. You want to be able to do that in situ. So that's really important. When we think about the roadblocks and capabilities, power is certainly one of them, right? And you rightly described that, sir. And so we got to have some more efficient power systems. Deploying enough infrastructure into space is also a key. And you know, you're at the sweet spot, kind of a chicken and an egg. Do you deploy the infrastructure before the operational use case is there, or do you wait until the operational use case? And the industry is kind of finding its way on that. You know, a little chicken, a little egg, a little chicken, a little egg, as we start to build that out. And so, you know, being able to move enough capability infrastructure into space is going to be one of the pieces as well. The other piece is going to be creating the orchestration and integration layer, because now you're not talking about a single transport system. You know, when we talk with the team in the other room, when you talk about the outer net, it's not a single company, it's not a single government, it's not a single government agency. You're going to stitch together hundreds, if not thousands of nodes, disparate companies, countries, technologies. You've got to have an orchestration layer that integrates and interoperates all that capability. And we're starting on some of that today, but there's still a lot more to do there. So those are about three things off the top of my head. I'll add a fourth, and that's security, right? Because we live in an environment where I wish we didn't have to secure everything, right? I wish we didn't have to, but we just do, right? There are threats out there that range from, if it's not a hostile military or intelligence threat, it's a bad actor in the financial spaces threat, right? So there are enough threats out there that you've got to bake security and all that ahead of time. And so we're going to have to come up with some new protocols in terms of identity access management. On the AWS cloud, we have today where if you build a cloud-enabled capability, you tell me who you want on it, you tell me who you don't want on it, and we can design that for you, right? We have to modify that a little bit, you know, for hundreds or thousands of nodes across space users in different countries and that sort of thing. But we know how to do that. But that's one of the requirements too, is optimizing the identity access management and security protocols. So there's about four. I hope that helps answer the question. Yeah. Maybe one last. I know it's been a long day. Or none. That's okay too. All right, great. Hey, thanks for having me. I really appreciated participating in the workshops. I appreciate DIU. I appreciate all these organizations coming together. To the stars, through the cloud. Thanks.